My name is Mark Davis. I'm a distinguished engineer with Dell Software Group. Dell Software Group is a relatively new entity, and you can see some of our entities right here. They've been, Dell Software Group's actually only about 2 years old, and we grew by acquisitions, and including my company, including several of their companies, and I'd actually like to welcome StatSoft, which is our newest acquisition, to the Dell Software Group family. We hope they have a long and storied membership in Dell Software Group. The topic that I have today is big data and the challenges of unstructured information analysis. So unstructured information is, has various definitions to various people. One of the definitions is anything that you don't put in an RDBMS, therefore it's unstructured because we haven't created a schema associated with it. In general, however, we like to call that semi-structured because it has an implicit schema associated with it, whether it's sort of tabular data coming out of log files, which were one of the earliest and most canonical Hadoop use cases. And we'll reserve unstructured information analysis for things like text analytics. Some of you who may have been in the last session in here saw a little bit about that. But I like to always begin with a big picture sort of point of view on this. And, oh, there's the big picture. You have to silence your cell phones. Sorry about that. And so the agenda here, I'm going to talk about industrial revolutions and economics a little bit, and then big data, and sort of give a framing for why especially unstructured information analysis is relevant. And then we'll dive directly into text analytics use cases, cases that we see out in the real world, out in the industry, more and more coming about all the time, and how we can create structure and metadata out of those unstructured data resources. Next, text analytic approaches. We'll talk about some of the ways in which we can extract meaning and create new metadata out of the data. And I have a little sub-bar here. I saw there's somebody, the next talk that I want to go to is on regularization, and which is a fascinating topic in machine learning. I wasn't altogether sure whether we should do really deep and interesting things, but I'm going to try and talk about something that's kind of deep and interesting here for a little while. And then finally, just talk about integrated solutions. Not going to do a demo because we had some video hookup issues, so we'll just focus on the slideware instead. So I'd like to start off with talking a little bit about industrial revolutions and a little bit about search. And what do we mean by that? Well, so there is an argument that's based on estimating the number of people who are alive from the earliest people and how much they talked, and if they talked a certain amount of time each day, and if you were to encode all their voices, how much data would we actually have? And the argument is that it might be an exabyte up until about 1900. And most of the data growth then, the things that we call data today, has occurred since then and grown out of all of these different machines that we have and all of the different text that's being generated. And it's really exploding now, as most of us know. We're generating something on the order of a zettabyte of data or more on a yearly basis, the entire data universe. A lot of that is digital video and things of that nature. So we see this incredible explosion, and this is why people are interested in this topic of big data and big data analytics and so forth, because these scales are getting enormous all the time. But what is the real impact that's going to come about for this? Well, R.J. Gordon, who's down here in the corner here, he's at Northeastern University, and he's a pessimist. He's an economist, and by their very nature, economics is called the dismal science. And it's called the dismal science because it's about scarcity and about not having enough, and how do you sort of try and optimize that. And so he did a study, and it said, is U.S. economic growth over? Faltering innovation confronts the 6 headwinds. And as I say, it's a sort of a dismal read. But he says almost all major economic change that's taken place in the United States and the world has come about due to industrial revolutions. The first industrial revolution was steam power and the ability to replace horsepower with steam engines. And in fact, James Watt actually decided to use horsepower as the measure for steam engines, specifically so that he could make a value proposition argument to people with teams of horses that they could replace this with a steam engine. Industrial Revolution number 2 then comes about just after the turn of the century, and we have rural electrification, we have telephony that becomes widespread, radio, we have communications, and we also have sanitation that becomes widespread. And there's anecdotes about how New Yorkers would cheer as the sanitation workers came through during the parades in the early days, because they were just finally just happy to have the streets clean for a change. And Industrial Revolution number 3, we have the World Wide Web, we have personal telephones, which of course are silenced, and we have communication between machines, machine communication. And at this point, R.J. Gordon says, that's it. We're doing this, when we go in our kitchen during the day, we're cooking the same way we did. Yeah, you have microwave ovens, but it's basically the same thing that we were doing back in the day. A cell phone is just a glorified radio. It allows a little bit more coordination in society. Maybe that was an industrial revolution, but there's nothing more to come. Nothing that he could see. So there's, in contrast to this then, Paul Krugman, who got a Nobel Prize, or a fake Nobel Prize, as some people say, the economics prize is not a real one, at the New York Times said, well, maybe Industrial Revolution number 4 is the big data revolution. And how does that come about? It comes about through having sufficiently large data sets available that you can overcome some of the brittleness that's been traditionally associated with intelligent technologies, intelligent systems, in such a manner that you're able to produce systems that are that move the economy into the next level. Now, of course, industrial revolutions come with an enormous cost associated with them. They break down traditional roles, they break down traditional work relationships, and they displace people. Traditionally, this has not been a major problem. There's, for example, there's lessons learned like not a single steam locomotive producer made the transition to diesel locomotives. They were all new and so forth. But that sort of creative destruction resulted in a whole new industry and greater efficiencies and so forth. So if there is a downside to it, there's also potentially an upside to it. And so what are the technologies now that we're seeing that are emerging out of this potentially fourth industrial revolution? Well, they're built around data analytics that are operating primarily on unstructured information and looking at the patterns and the contents and the semantics associated with that unstructured information, which brings us to the topic of the day. Text analytics use cases. So I got my start in terms of my academic career working in this space, and then my company was actually also funded in this space, where we want to be able to improve the effectiveness of military forces, and we're going to use to do that a wide range of information. For example, we have situation reports that are manually generated by the officers and the non-commissioned officers at the end of every engagement, after action reports as they're called. We have other types of memos that are flowing through the defense system, as well as the traditional types of human intelligence and signals intelligence and so forth that are moving through the system. Well, with regard to the situation reports and this acquired so-called multi-source intelligence, one of the things that we want to do is take the narratives that are expressed within that about what happened, who was there, what happened, who was encountered, where it took place, and so forth, as well as the semi-structured and structured information attached to those reports, such as geospatial coordinates and so forth. And we want to extract them. And so you'll see this theme a lot in the remainder of that. We want to extract named entities and relationships. We want to classify and label the data. We want to normalize geospatial and temporal metadata. And we want to visually understand relationships and trends. And the end goal is to identify mission objectives and to create priorities so that when you take a look at doing your next mission and you have to go to a small town, you want to look at every single report that was associated with that town. You want to understand the roads and the road system that are leading there and everybody that was encountered in the past so you can understand what you're getting into. The better you can do that, the lower the chances of difficulties arising and the better your ability to apply force effectively. And over on the right, you can see your right, stage left. You can see the multi-source intelligence extracting from the data metadata, entities, and relationships, and ultimately achieving visual understanding with regard to that. The same sorts of rule applies to competitive intelligence then. In this case, the goal is to become more competitive as an organization, as a company, and that means that you're going to use a different sort of sources. We're going to use, for example, patents. We're going to attempt to mine the patents to understand what our competitors are doing, to think about how we can position ourselves with regard to that, maybe to do collaborative work with them or competitive work. We're going to look at PR announcements, legal documents, white papers. We're going to crawl their websites potentially if they'll ethically allow us to do that under the rules of the road with regard to robots.txt. And then we're going to extract named entities and relationships. We're going to classify and label and visually understand relationships and trends. The domain may shift. For example, if you're an electronics company, you may want to extract DDR3 and DDR2 memory types. You may want to extract what products those are being used in and aggregate them together in such a way that you can actually make sense of that data and drill down more effectively rather than just doing Google searches and trying to understand everything based on ranked list of results. And our goal then is to change R&D priorities and improve marketing approaches. Again, the value chain over there on the other side shows how that might work. Excuse me. Drug discovery. The goal here is to discover new drugs, to detect side effects, to speed R&D. We're going to use published research reports. We're going to use patents again. We can now see the patent applications actually flowing through the system, which is helpful. Adverse effects databases. It turns out that the United States Food and Drug Administration actually maintains a database of adverse effects. And every time a physician, a patient of a physician comes in and says, this did something to me, I'm losing my hair, my eyesight is going, etc. They are supposed to enter that into the adverse effects database. And I mentioned this because I did actually mine this thing, and there are some very curious renderings in there. One thing that we encountered was a statement that said, "It made me feel like a dwarf." And outlier, I don't know. Genomics and proteomics databases. So another sort of anecdote with regard to this, up at Stanford Medical Center, there's a researcher there who's working on genetic abnormalities that result in strokes within brains. And she said that she basically just spends all day with an Excel spreadsheet. She takes whole proteomics dumps, which is a massive amount of data. She tries to correlate it with genomic information coming from the National Center for Bioinformatics, NCBI, and all of these different GenBank accession numbers and things like that, and just spends all day in Excel trying to make use of it. And she said, anything you can do to help, please. Okay, here's a much more focused marketing example, and this is buy signals. And there's a lot of players who are working on this. We want to identify what people want to buy. We want to direct them towards the things that they'll buy with a greater degree of facility. We can use social media where it's public and available. We can use blogs, websites. We can use other types of information about demographics where that's available. And we want to extract, for example, sentiments. And so sentiment analysis is a very popular topic in text analytics now. We want to classify and label with normalized spatial and temporal metadata, and ultimately visually understand trends and try to catch. One thing that we can do here is not just buy signals, but also try to detect negative signals that are coming from the marketplace. For example, if a product is being poorly received, what are the reasons for doing that, and can we correct it? Colleagues of mine within Dell have canonical examples of this, where a Linux-based laptop was released, and the Linux-based community, their sales were much below what they intended it to be. And so they analyzed the social media data, and they realized that people were simply rejecting it because the Linux version was more expensive than the version with Windows on it. And so people felt hurt as a result of this. So they just adjusted the price points a little bit, and sales improved very rapidly. But our ultimate action is to target sales and enhance our offerings to our customers. Legal informatics, here's another area. This is actually a fairly crowded space, but we want to find case supporting and actionable information to be able to go through the legal process, whether that's discovery and prosecution and tort and so forth, email repositories, office documents, patents, memos, and things of that nature. Again, extract named entities and relationships, classify and label, and visually discover trends and relationships, with the ultimate action to develop legal theories and prepare for arguments. And there's a number of other ones that come up constantly. For example, customer relationship management is another one, where you want to look at the data within your CRM system, which includes narrative descriptions on the part of phone bank operators and so forth. And often it's unstructured, and you want to be able to extract meaning from it and understand sort of what the categories of problems with your products might be. Okay, so given that, what are the approaches that we can use to begin to look at this? And it turns out that this is a very interesting sort of area of analysis that dates back, amazingly, to about 1989 or so. And that's when the big war began. So what is the big war? Well, statistical methods versus linguistic methods. And so the linguists got a hold of computers, and they said, we got to use the computers to create to simulate linguistic processes, grammars, Chomsky, all of these different things, and we're going to be able to just solve every problem. There was actually it dates back even further than that. In the 1950s, there was a prediction on the part of the father of information theory that it was only a matter of time, 10 years, and computers would be talking, because it was just, a very simple problem to undertake, and they would just knock over all the problems and so forth, and it would be done. In the late 80s then, some folks at IBM Research started to do statistical machine translation, and they made remarkable headway very quickly, and the linguists threw up their hands and said, apostates, and this teaches us nothing about language and so forth. And as it turns out, that same, more or less, technology is the basis of Google Translate for all its flaws and everything. And there is an example there where the system has, through the use of big data and through the use of relatively simple statistical analysis methods, come to be fairly good at, with all the limitations, of course, that come with it. So let's take a look at the differences between these, and then we'll continue to dive down into how these things work. So the linguistic methods are all about understanding language based on the perspective of linguists, and you use linguistic concepts to create computational systems. That is, you look at the way in which grammars are formed, and you try to build systems that will will follow that model. Statistical systems, on the other hand, are data-driven, and just consider language, and this is where they're apostates to the linguist. Language is structured information. I got my academic start over on the far side, the right side there, and I dearly remember when folks would stand up in conferences and yell, and they would say, "But you don't care about language," and they'd walk out and storm out and so forth. And it just goes to show that academics will argue about anything because it doesn't matter. But in reality, what happened was, regardless of the red versus blue war, is that people are pragmatic at the end of the day. And so there was this hybrid version that emerged from it. And that is that, yes, we understand language some. We understand what parts of speech are, for example. And we also use statistics and machine learning on top of that to help improve at the areas where we cannot get coverage associated with those. So what does this look like in detail? At the bottom of the stack, when we're doing these kinds of analysis tasks on unstructured information, we're going to tokenize. That is, we're going to split up the language into the individual tokens that are meaningful for that language. This can be remarkably complex. For example, Turkish is what's called agglutinative. German nouns are agglutinative. They tend to glom onto each other, and you have to split them up in a linguistically significant fashion. As it turns out, there is disagreement among Chinese linguists as to what constitutes a single word. And this is not uncommon. Once you tokenize language, however, then the next step is lemmatization. And lemmatization is a fancy word that just means finding the dictionary head word. That is, for ran, that's the past tense of run. And so the head word in the dictionary is the thing at the top. And then the other words are variants on it. So that's lemmatization. Again, cross-language gets very, very complex very quickly. Irregular verbs in English are very complex. Language learners who come to English complain bitterly about and tend to make mistakes. Children make remarkable mistakes associated with irregular verbs in English. But other languages, of course, have remarkable difficult problems as well. The next step up is parts of speech tagging. That is, can you identify, based on the context and where the word is within the sentence, whether it's a noun, verb, prepositional phrase, preposition, etc. We often use, most of the methods that are out there actually use statistical methods for this. Hidden Markov models, for example, and other methods based on very similar techniques, conditional random fields, and some of these things. And what we do then is we're building a statistical model that essentially predicts the part of speech of the next tag based on the last tag and the surface form of the word. And so those methods are typically done using statistical means. But then we fall back again and we say, well, once we get these words and their parts of speech and so forth, how do we combine them together so that Mark Davis, we now know, is a phrase, and then ultimately it's a person's name. And when we see Mark, after we saw Mark Davis at the beginning of a sentence, we don't think of the 13 other meanings of Mark, like marking up a piece of paper and a mark of dishonor and things like that. I hope you don't think that. And so we do finite state transducers on top of that. And what is a finite state transducer? It's a regular expression rule that simply says that if these things coexist together, if this one precedes that one, if this one precedes it, and if it has a capitalization at the beginning of it, all of these different features of the content result in the production of additional metadata that labels that thing. But it doesn't always work. For example, you may not know the entire list of all known corporations in America. And so when Engorsian, Inc. comes up, you have a guesser in there. And so we're falling back to statistics again and finite state rules, where the fact that you have a capitalized word followed by an Inc. is highly indicative of a corporation name. And these patterns for titles and mountain ranges and so forth tend to kind of fill up the slack associated with having a complete, what's called an onomasticon in the formal language, but that's just a really fancy word for a collection of nouns, in other words. And one of the things is that you can cascade those guys, and so this whole space is called cascaded finite state transducers, and it tends to start slowing things down. So the reason we're getting to big data now to do this is because as you look up this entire stack of technologies to do this sort of thing, the computational load and the cost associated with doing them is getting more and more expensive. And even at the end of the day, you get to the end and there's things that you just get wrong. These technologies get things wrong. And so what can you do to fix it? Well, you can use machine learning at the top of the stack. You can learn that the patterns of mistakes that your system has been making, often these are errors in what's called recall. That is, that you found a lot of things that you knew how to find that were in your onomasticon very, very clearly, and you've labeled them correctly. You have high precision. It's the new things that you've never seen before that are the problem. And so machine learning can help to fill up that gap. Oftentimes it results in a dulling of precision as a result of that. So let's take a look at what this looks like. Maybe a little hard to read here, but this is a pack from our Katenga Analytics Suite product that is being operating over text. And this is an old document about from the Wall Street Journal. And what it's doing is it's identifying locations, job titles, persons, negative sentiment terminology, product launch patterns, product sold patterns, legal action patterns, mergers and acquisitions sorts of activities that are going on. And by extracting these all and then labeling them, and allowing for labels to overlap. For example, you can see First Boston merger stars, Bruce Wasserstein and Joseph Perella, with overlap within it. You can generate metadata that can be useful for all of these different types of tasks that we discussed previously. However, without having a delivery system to be able to consume this kind of rich metadata, we're still going to be at a disadvantage with regard to how we do it. I mean, labeling it all demonstrates its effectiveness, and you can, as you scan through, you can actually see some errors that are occurring in it, and we may need to correct those errors, filter them in some way. But ultimately, we're going to need some way of making this accessible to people, and so we'll come to that in a little while. But one thing I wanted to put in here, because I have the time, because of a demo limitation with the dongle here, is I wanted to talk a little bit about what else we can do on top of the methods. We're doing named entity extraction, finite state transducer cascades, to be able to generate this metadata. But what if we wanted to ask the question, different types of questions? What is the relationship, the semantic relationship between two different pieces of text or two different pieces of data in some way? And so I'm going to talk a little bit about implicit semantics. I don't know why the font got messed up there. So there is a very elegant method that's highly applicable to big data, and I bring it up because I like it a lot. And it's based on some analyses of the way in which human beings appear to store information within our neural networks. And that's called random indexing. It was invented by some folks at the Royal Academy University of Sweden, I believe. And it's very, very simple. And random indexing, so the best part about it is that you're assigning random numbers to things, and then you're getting smart stuff out of that. So what we do is, for each word that we have, or each token, what we're going to do is we're going to assign a random sparse vector. So maybe with about 1% or 2% of the bits turned on, or integers, if you want to use integer vectors. It actually doesn't matter that much. And then each time that we encounter a word, we're going to sum up all of those random vectors that occur for all the words around it. And we just add those together. We have to be consistent. So when we see the, that it's got to have the same random vector each time that we do it. So we can't assign new ones to it. And that actually brings up an important consideration we'll see in a minute with regard to big data. And what happens then is that words shall be known by the company that they keep. That when we see past big data analytics, we see the mentioning of the Microsoft stack, we see all occurring within the same context, and then we see another Strata conference on analytics, and we see similar words, analytics, we see Hadoop, we see RDBMS, and so forth. Those two will tend to cluster together because the related contexts have the same vector patterns associated with them. And so this is remarkably simple, and it's also excellent for big data applications. And that is because we are simply creating finite vectors that are maybe 3,000 or 4,000 bits long for each word, and we don't need to maintain massive document by word matrices and some of the other techniques that can do similar sorts of things. We just add these guys up and compare them. And so why would we want to do this? I mean, it seems simple enough. Why would we want to do this? Well, I mentioned before that this was invented actually as a model for human and animal sparse memory to kind of simulate it. And it was remarkably effective at simulating it. And so here's an example of how remarkably effective it is. That anybody take the test of English as a foreign language? No? Okay. So when grad students come to the United States to do grad school, they'll often take the test of English or the TOEFL test as a foreign language. And as it turns out, by doing this and using these methods, you can actually achieve higher rates of success than the average grad student coming to the United States. And all we're doing to do that is you take the text that the TOEFL test taker is supposed to read, you sum up all of the sparse vectors of all of the words, and then when they have a question that says, the meaning of longitudinal in the third sentence is most closely related to A, B, or C, and you simply compare the vectors of the answers to the original text and find out the one that's closest to it. And voila, it appears to work with remarkable fluency. So they came, these folks at the Swedish university came up with this notion of distributional hypothesis, and that is very simple. Words with similar co-occurrence patterns have similar meanings. And this goes back to Wittgenstein and words shall be known by the company it keeps. That's a quote. That's actually not from him, that's somebody else, but close enough. And amazingly, there's some really cool mathematics behind it too. And so the Johnson-Lindenstrass lemma simply says that if you have really sparse data, and words are really, really sparse, we use a lot of words most of the time, and then most words we hardly use at all. And they come up in New York Times articles, and that's about it, and TOEFL tests and things like that. But what you can do is you can just, if you multiply the matrices of these things, it preserves the relative distance as long as we have this high dimensionality associated with this. So this is an example, those of you who have a machine learning background, where the curse of dimensionality actually works in reverse, that it's a blessing of dimensionality, if you will. And also, the other cool thing about this is that we're using these fixed context vectors that I mentioned before, just like something on the order of 4,000 bits. And that reduces complexity. And this is very versatile. I've used it for word-word context, Word document context, entity-to-entity context, so another hybrid approach where we're initially doing finite state transducers, we're doing name-to-entity extraction, we're creating these entity relationships, and then we're looking at the context in which they occur using the same sort of thing so that you can see who is similar to whom in much the same way as a recommendation engine might use prior buying patterns to point to possible recommendations. There are some challenges to doing this. For example, doing a MapReduce version of random indexing requires a reduce phase that merges these random spaces together. Or you can pre-compute the sparse word vectors and have them live in the context of each individual node. Or you can serve the map phase from a common term signature service. So you have the central database that everybody's feeding off of. That kind of defeats the purpose of Hadoop and embarrassingly parallel sorts of process. Or we can use a really good, more or less complete hash function across instances and compute a sparse vector to be able to do that. And so what are the applications of this kind of semantic technology? Well, we can cluster terms, entities, instances, documents. We can create auto-suggestion systems that go beyond just using the prefix that you are entering into the system, but actually suggest things based on semantic relationships and other people's use of the same sort of terminology in the past or related terminology. We can use it for categorization of text occurrences, categorization of blog posts, and things of that nature. And abstractly, it's a generalized similarity determination engine. So how do we consume, then, any of this stuff? Now, I've talked about some different techniques, these hybrid approaches, the generation of metadata, similarity engines, and so forth. Delivering that, though, requires some sort of rethinking the way in which BI is done. And that's one of the things that we've been working on for several years here in Dell Software Group. And we're integrating with our new acquisition, StatSoft, as well, to try and deliver even more of this sort of thing. Well, one way that we can do it is by combining together search and analytics. And this is where I get back to search and the big data sort of revolution, insofar as there is one. When we come down here to the bottom now, in general, we're doing metadata extraction. That's one way to look at it. We have documents. We're creating semantic metadata on those through something like random indexing, maybe. We are creating named entity metadata, who, what, where, when, why, which are called the W questions with how thrown in. If you ever ask a linguist, it's an inside joke. Those are the WH questions. Once we have that data and the original content, we can index it into a search engine form, a distributed search engine form, where it's then amenable to be able to be queried. And we then build on top of that query capability spell checking by looking at the individual entries within the corpus that we've analyzed, and auto-suggest capabilities on top of that. And then what takes it, though, to the next level where we're starting to get analytics is the idea of faceted search and facet browsing and facet charting, where now when I do a search on a company on Dell, I'm not just seeing a ranked list of results, similar to what Google does, but in Bing, since it's in Microsoft. I was formerly Microsoft, by the way, so I'm not saying anything negative about Microsoft. But instead what we do is we take all this rich metadata and we bind it into these visual tools that allow us to drill down on the data in interesting and new different ways. And this is a term, I believe it was invented by Marty Hurst, who's now at Berkeley, of faceted search, and it involves browsing and charting. And then finally, resource integration, where we're integrating different types of resources together into the system as a whole. So let's take a look at an example of this. Here we have from the Dell Software Group's Katenga Analytics Suite, slightly out of date slide here. But what we've done is we've crawled through Facebook and Twitter associated with different topics. We use the publicly available APIs for both. You have to plug in your own application credentials in order to make this happen. And then we can make a topic like Malaysia or Olympics And the big data technology under the covers is going out through the publicly available APIs for these guys, harvesting the posts that are associated with the given topic, and then bringing it back in and doing the same kind of text analytics that we've talked about before. The analytics involves running it through the full pipeline associated with tokenization, associated with named entity extraction, and preserving the existing metadata associated with the tweeter and the Facebook poster, their identity, as well as other types of information, but at the same time, extracting out of the main content the primary sentiment-bearing terminologies that may be found there, including things like bad and you love the Olympics and it's great and it's good and so forth. And this visualization form that you see in the middle actually comes from D3 if any of you are familiar with it. But it's called a pack tree visualization. And it supports the ability to see at a glance the relative distributions of the individual items as well as the global distribution or mass associated with them. So you can see positive sentiment here is shown at, it has a much greater representation than negative sentiment. We can see the distribution over time. So we can bind the temporal metadata, the time and the place, directly into a heat map that shows how, over time, did the sentiment change as it was going. And we scroll down a little bit, and you can see that there's a map embedded in there. So we can see where people have allowed within the, for the Twitter posts that they've made and so forth, they've allowed for a location-driven metadata, and some people do, especially when they're using their phone, that we can map that and we can look for patterns then based on that metadata. We can actually drill down and look at individual posters, the individuals who tweeted the thing, and filter by them and look at their subset. And we can search over it now. And this gets back to the main theme of search integration with analytics built in, that there's a search box up at the top. And you can just start typing, and you get recommendations for completing your search, and you can drill down based on that. So you can use that as an entry point, and then you can use these other tools to be able to understand the lay of the land and to do deep dives in charting and so forth. So I think I'm right on time. Of course, 15 minutes for Q&A is probably a little too much, but could be. So in summary, big data search and analytics has many unique challenges. We have this problem associated with volume, variety and velocity of data. But our focus here was really on more the variety crossed with the volume question, and that is, how do we extract structure from unstructured information? And we're doing that through a combination of things. We can use machine learning to do it. We use machine learning in some cases. We use human intelligence through the presence of UIs with visualizations that people can use to drill down on things. And then some of it is about knowledge engineering, the rule systems, the finite state calculus that's used to do some of these tasks, like what is a telephone number? What does it look like? What does it look like across all of EU? Being able to extract all of those sorts of patterns is really a knowledge engineering task and requires human intervention in order to set that up initially. And for us, Hadoop processing enables each of these aspects because we're fundamentally doing some heavyweight stuff here in order to get the job done. And so being able to distribute that and make use of multiple machines is extremely important. And I have another anecdote here. I was working with a company up the peninsula here in around 2008, and we were using an ontology that they had created with regard to medical terminology and all of the different ways in which people talked about cancer and the subcategories of cancer, and then all of the findings in the literature that were associated with that subcategory of cancer. And in order to create a faceted search experience, it would take us about 4 days to run 20 million abstracts through the system to annotate them with this kind of data and then index them as well and so forth. And you get to the end of it, and it just drives you nuts, and you want to make one change to the way in which something is expressed. And so you go in and you find that, you see it, it's staring at you, and then it takes 4 days to run through it again. But and in 2008 even, it was just on the cusp of having this widely available tool like Hadoop that allowed for distributed processing of these things and the ordered aggregation together of the results. And so prior to that, when we encountered these sorts of things, we would write our own. It was roll it yourself. Shell scripting with remote shells, and sometimes people use Beowulf and MPI and some of these other distributed technologies. But then we have Hadoop, and we're able to exploit this. These processes are, for the most part, capable of running in an embarrassingly parallel manner to do this kind of annotation. And we can enable complex user interactions with big data on a self-serve basis. And this is one of our key themes that, although under the covers there's a lot of complexity associated with computational linguistics and natural language processing, the enrichment of the data, some machine learning, and so forth. Ultimately, we want to get to a point where people are using tools that are familiar to them in terms of their engagement with data. Search, click, point, click. One more anecdote, and then I'll stop with the anecdotes and go to questions. My friend Sue Dumais, who's a researcher, I think she's still there at Microsoft Research, she found in 1989 or 1990, she did a study of search engines. And back then, the only people who cared about search engines were spies and librarians. And so they were all the funding, and librarians don't have any money, so all the funding was from spies. But what she studied was, she said, well, what if we have a ranked list of results and people have to type in queries, just like we do with Google? And so they type in a query, and then they get the results, and they read through the results, and they say, it's not exactly what I wanted. Instead, what I'm going to do is I'm going to change my query. And so you type in some additional words, and you press the search button again, and you get some more results. And, okay, yeah, I'm getting close and everything. And so she said, well, what if we did this funny thing where you just had this more like this button under each one of the abstracts? And it seems, obvious now. But you press the more like this button, and instead of having to figure out query terms, you use the more like this to be able to look at related documents. And she said, well, how can I study this? And she's a cognitive psychologist. And so she said, I bet there might be a correlation between people's ability to think about words and this. And how do I measure that? So she correlated SAT scores of her subjects with their efficiency in using the two technologies. And she found that, sure enough, your ability to reformulate a query is directly proportional to your SAT verbal scores. And then she found another result. That effect goes completely away if you put the more like this button on it. That people can look then and say, I don't know words very well, but this is me. I'm not saying you. I don't know words very well, but I'll just press this button, and yeah, and they get the same results out of it at the end of the day. And so, an example of how we can enable complex user interactions with big data on a self-serve basis, and we can help analysts discover and use big data by providing this kind of unstructured information analysis capability. And with that, I have 10 minutes, and so, yes, sir. Yeah, it's called a heat calendar. Good question here. Yeah, it's called a heat calendar. And so you can see here, this is for 2012, and each one of the months are going across in the larger blocks there. And the reason that they're funny staggered is because of the days of the week end on the month in different ways. So that's on the left there, that's the first week of January, the second week of January, et cetera. And then the color blocks in there represent the aggregate sentiment score where we have the information available for it. Yes, sir.
On your summary slide, you've got the 3 V's, volume, variety, velocity.
Yeah.
And IBM, like the throw veracity in there. I'm sort of wondering, when you do all this text search and you drag all this association up, if somebody puts in a whole lot of text that they wish to manipulate the results with, given that to be done by false or whatever,
Yeah.
how do you take into consideration that the whole world is suddenly told it's on fire because somebody's lobbing out lots of information about fires and
Yeah, spamming the system, right? Yeah, so there's a couple of, I mean, the fundamental issue even before that is, oh, yeah, sure, sorry. He was asking if, I'm supposed to do that, it was on my sheet here, actually. He was asking that if you have this large text corpus and you're extracting insights from it in some way using these sorts of technologies, what if somebody games the system or spams it in some way? Is that accurate, sir? Yeah. The veracity of the data. And how do you cope with that sort of thing? And it's a real problem. I think that as these intelligent systems actually become more and more a part of our lives, that you're actually going to see, this kind of race between spammers, nefarious parties, just like we see with regard to security and spamming in email. It's a continuous battle to do it. In some cases, you can look at regularity associated with the data, but and detect these kinds of outliers that start to bloom. There is a whole academic topic that's made its way into some commercial technologies that's called topic detection and tracking, where you actually are looking at, you're essentially clustering using something like random indexing, all of the content that's coming through, and then you're watching for the emergence of new topics. And so when the Olympics comes up, suddenly everybody's talking about Olympics. They're talking about, all the very important sports like curling and things like that. And then that dies down again. And nobody talks about curling for 4 years. So the ability, I apologize to the curling fans. Yeah, topic detection and tracking, but I think ultimately, very skillful and nefarious parties will be able to manipulate the underlying distribution, and they will go out of their way to do that. Finnish kids with too much time on their hand, I don't know. Yes, sir.
How do you deal with sarcasm and those kind of linguistics that don't have the polarity?
Yeah. So the question is, to follow my notes here, how do you deal with sarcasm and other phenomena like that? Yeah. So this is the linguist, and they would say that it's an area of linguistics called pragmatics, and they would say that statistical methods can't really capture that because they're just looking at regularities. Sarcasm is a uniquely human phenomenon, and you get prosody when people are speaking. Is that a real question? It's got a certain spike to it in English at any rate. But fundamentally, it's a problem. So one way you can deal with it, though, is through machine learning layered on top that is looking at those sorts of categories. And I'll just point out, one of the challenges that we confronted when doing this was exactly those kinds of pragmatic things. Not only things like sarcasm, but things like in English, the use of a bad, for example. Bad, the music was bad. It means good. It means great. And so what we actually did was we put a k-nearest neighbor learning algorithm on top of this, but we didn't tell anybody what it was. Instead, what we do is we have where you're setting up your model, you can vote up or down on individual posts. And you can say, this is relevant, this is not relevant. And then gradually over time, it takes those votes and it looks at, for each new post that's coming in, is it closer to the irrelevant than it is to the burgeoning collection of the relevant. And then it's basically an ensemble of decisions that layers on top of that. Unfortunately, there's no magic bullet. That's one approach to it.
And then just a follow-up question in terms of different variations of the language, like the British language, US language, certain words have different meanings, like you said that, but one that comes to mind is like mad. Mad in British means, you know, bloody.
Yeah.
Bloody, yeah. How do you, is that, do you take into consideration like the geolocation of the tweet and say, okay, this must be a British, so you use a British kind of dictionary or lexical database?
Yeah, by the way, I don't cuss in British. Yeah, so that's one technique. But so this, in general, the kinds of things that you're talking about, I should repeat the question. How to use regional variations, and do you take into account geolocation information? You can, we do not at the moment. We have only one way of sort of correcting for things, and that's based on this simple machine learning that could be applied to anything. But there's sort of only one model that you can use. It's good or it's bad. But in general, what we talk about in sort of computational linguistics is the idea of microtheories. And so you have a microtheory about sarcasm, and you have a microtheory about geolocation and linguistic variations across different languages or within language groups. But it's a one by one. Yes, ma'am.
Well, what do you think about sort of making a table of words to ignore? Did you already say that?
Oh, absolutely. So, yeah, it's a very common thing. It's called a stop list or a kill list. And
Or anything that is that ambiguous,
Yep.
that hard to just ignore it. And
Yep.
the other things.
yeah, so by default, a lot of the methods that are involved use what's called inverse document frequency. And so words that occur everywhere, like the and a in English, they just go away. But then in addition to that, yeah, you can use a direct kill list to just get rid of those. There's a question back there. The other man.
IBM advises us to use text analytics to explore raw data, so website logging files, actually raw website logging files, and then text analytics. Do you know that? IBM?
Yeah, I'm familiar with it. So if I can repeat it, IBM is advising you to use text analytics to explore log files.
Raw files, website logging.
Yes. Okay. So yeah, one of the things you get is you get this huge amount of log files that are coming out of it, and what tools do you apply to the task? You could try and clean that up and stick it into an RDBMS and so forth, but then you're confronted with the problem of having to manage the schema, having to do the ETL task associated with ingest, having to, and 6 months later or a year later, you finally get a system stood up, but the amount of data that's coming through is so huge that the expense mounts. And so, yeah, one way to do it, and it's a use case that we're certainly familiar with, is just index everything into a search engine format and slice and dice it a little bit. And then you can do raw pattern searches over it based on keywords. And if you can extract some better metadata out of it, for example, IP address patterns, you probably want to index the IP address pattern as a whole, index each one of the individual subcontexts so that you can search for all the 192s and things like that. Yeah, well, you're using it in a very shallow sense, but it's a great application that saves you often the pain and suffering associated with these log file analytics tasks. Yes, sir.
About extrapolating business process text data out of like user guides or playbooks or operational guides, and then trying to put together a business process visual map of that text data. Have you ever seen that?
Yeah, actually, I have. Just repeat the question. If you were to extract text and possibly metadata associated with that, and for business process purposes, and how can you then visualize and make use of that? For example, the U.S. Navy has been very interested in that sort of use case because they, for their purchasing chain of command, they have so many rules and regulations that it's extremely difficult to maintain that kind of knowledge base and to make use of it effectively. So they make mistakes all the time. Training is extremely difficult. And the amount of transactions that they're doing is extremely high. So they've been looking for solutions. I don't think that they've achieved what they want, but there's a number of these kind of mind mapping style tools and so forth that can be used to kind of visualize those sorts of relationships. And I think we have to wrap up then. I appreciate your time.